In this video, we'll investigate Ampere's law. So far, we've used the law of Biot and Savart to find magnetic fields due to currents flowing in straight wires and circular arcs of wire. We've also compared Biot and Savart to Coulomb's law. We see that they have common form except for the cross product in the law of Biot and Savart that doesn't occur in Coulomb's law. What we did find with Coulomb's law, it could sometimes be difficult to do the integration to find the electric field due to the differential electric field, whether the charge was continuously or non-continuously distributed. We'll find that similarity also with the law of Biot and Savart. So the symmetry we analyzed using Coulomb's law was planar, cylindrical, and spherical symmetry, and in those applications, Gauss's law proved to be a good way to find the electric field and the relationship between electric field and electric charge. So similarly, we will use, to Gauss's law, we'll use Ampere's law in such symmetric situations. So if we compare then Ampere's law to Gauss's law, we see Ampere's law has our line integral of B dot ds, and that's equal to the encircled current multiplied by the permeability constant. Whereas our Gauss's law was a closed surface integral of E dot dA, and that was equal to the charge enclosed by the surface divided by the permittivity constant in a vacuum. So if we compare the two, what we called a Gaussian surface we'll refer to as an Amperian loop because it's just a line integral. So our closed loop is a loop of integration, whereas our surface integral was really a double integral around a closed surface. We use the same subscript ENC. ENC means the current encircled. ENC in Gauss's law meant the charge enclosed. We know that charge can be both positive and negative, and that falls out of our Gauss's law. However, current can flow in one direction or the other. It can be positive or negative depending upon the direction of flow. So that direction of flow needs also to be considered when we're doing our closed integral of B dot ds equal to the permeability constant times our encircled current. So the sign of that encircled current has a dependency upon the direction of integration. So if we have our B dot ds, in what direction are we going to go around our direction of integration around whatever our line of integration happens to be? So we need a law then, of course, to say how does that direction of integration relate to whether a current's flowing, in this case, out of the page at us or into the page away from us. So the law here is, again, another right-hand rule. So we'll curl our right hand around the Amperian loop with our fingers pointing in the direction of integration. And when we do that, if our thumb is pointing in the same direction of the current, which would be here, then we'll assign that current positive. If our thumb is pointing in the opposite direction of the current, we'll assign that current to be negative. So that's our law for the relationship between our encircled current here and our direction of integration, where we get our direction of our ds. So if we apply our Ampere's law to this general situation, in this scenario we have three currents shown perpendicular to the page, I3 with a dot pointing towards us, I1 with a dot pointing towards us, I2 with an X pointing away. And we choose an arbitrary Amperian loop, looks sort of like a peanut here. And the current direction says it's also arbitrary, but it may very well be defined. So from our direction of integration, then we'll mentally divide our loop up into little ds segments. As we go around the loop, we have our little ds segments. They completely changing direction around this non-symmetric loop. We also know that our magnetic field is in the plane of the page. We know that because the currents are perpendicular to the plane of the page, but we don't know the orientation of the magnetic field around this loop. We don't have any symmetry to be able to determine how these sum yet. So, but the direction of B is arbitrarily shown here. If this was the direction of B at this point on this loop, then this angle theta here is the angle between our ds vector and our magnetic field vector at that point. Then our scalar product of our B dot ds then is just our B cosine theta ds, or it's the length ds, that component of B and the component of B tangent to the loop at that point. And then we can use our Amperes law to find our Amperes law is either the dot product or in terms of that theta, that angle, which may change. In this case, it would change as we went around this loop, and that would be equal to mu naught times our encircled current. So again, we can use our right-hand rule to determine the sign of the current relative to the chosen loop direction. In this case, if we use our right-hand rule, our thumb would be pointing towards us as we encircle our right hand around this loop. So our I1 will be positive, our I2 will be negative, and I3 is not included because it's not encircled, or it's not enclosed by our loop. In order to solve this, we need more information, but we could solve, if we knew I1 and I2, we could say that, you know, we have information about that closed integral about B dot ds. We know that's equal to the difference, our mu naught times I1 minus I2. If we had a more symmetric scenario, if we just had one current wire, and that's shaded in blue here, and we had a current that's uniform within that wire and it's pointing towards us, then what we found with our law of Biot and Savart, we found that their magnetic field was mu naught I divided by 2 pi r, at distance r, from the center of our wire. And our magnetic field had the same magnitude for all distance d equal to r in that case, if our distance was perpendicular to the wire. So it had the cylindrical symmetry about the wire. So we can take advantage of this symmetry as a circle to use our Amperian loop to simplify the integral. So our magnetic field, if we use an Amperian loop of a circle at some distance, lowercase r, from the center of our wire, our magnetic field then will have the same magnitude at each point around the Amperian loop. We arbitrarily can choose our direction to do our integration as counterclockwise in this case. And then our magnetic field is going to be tangent to the loop at each point. We know that from our law of Biot and Savart. So our magnetic field is parallel to ds or anti-parallel if we chose our Amperian loop to be clockwise instead. So in this case, our theta then is equal to 0. So our cosine theta is equal to 1. And our closed integral of B dot ds, or our B cosine theta ds, we can pull our magnetic field out of the integral since it's the same everywhere within the integral. And we just get the closed integral of ds is 2 pi r. It's the circumference of our Amperian circle. And that's equal to our mu naught times I encircled by Amperes law. So we can then solve for our magnetic field, and we get the same answer as Biot and Savart, yet easier than doing the mathematics involved in the law of Biot and Savart. If we take a look inside the wire, will we have a magnetic field? We didn't find that with Biot and Savart, but it's easy to find with Amperes law. If the current is uniformly distributed, then our magnetic field will still have cylindrical symmetry. And so if we choose an Amperian circle that's concentric to the center of the wire, our magnetic field will still be tangent to our Amperian loop. Since our current is uniform, then our current density is uniform, and we can find that encircled current through our definition of, that's our current density, I is equal to J dot dA. In this case, that's going to just be equal to our J times A. We can pull J out of the loop because it's uniform. The integral of dA is the area, and our area is what's encircled by our Amperian loop here. So that's our pi little r squared. But what is J? J is going to be equal to our I over A, or equal to our dI, dA, or equal to all of I divided by A, the area of the entire wire, right? So that's I divided by pi r squared. So our encircled current is some proportion of the total current And so inside the wire then we can get our closed integral of B dot ds. That's equal to our mu naught I encircled. That's Amperes law. Our B dot ds, again, cosine of B dot ds is going to yield a 1. So we just get the magnetic field times the circumference of our Amperian loop. That's 2 pi r. That's equal to our mu naught I encircled. Our I encircled we just found here. So we can solve for our magnetic field inside the wire. So we see if is equal to 0, we're at the very center of the wire, well, the magnetic field is also equal to 0. This is all going to be a constant, right? So as we increase, as we move out to the edge of the wire, we're linearly increasing our magnetic field. Outside the wire, we said we have the inverse relationship. So we can, in summary, if we have our current, uniform current flowing through a wire, uniformly distributed, we can find our magnetic field at R greater than or equal to R, and that we found with Biot and Savart. It's inversely proportional to the distance away from the wire, perpendicular distance. For R less than or equal to R, our magnetic field is proportional to the distance we are from the center of the wire. So we have increasing our magnetic field and then decreasing a magnetic field as we move away from the wire. So let's take a quick check. We'll compare the magnitude of our B dot ds. If we're comparing the magnitude of that closed integral of B dot ds, essentially we're comparing the magnitude of our mu naught I encircled. So we're really comparing, if we're comparing for these 4 Amperian loops, we're comparing the encircled current. If we look at Amperian loop A, we can choose it in either direction. Let's choose it's going in this direction. So if it's going in this direction here, and over here, it's going in that direction. We have 2I, so IA encircled is going to be 2I minus I, or equal to I. And we're just really looking at the magnitude. But if we look at loop B, this is actually going around behind that. So we're not including this current. So our IB is equal to, we can go in the same direction, but it's going to be equal to I minus I. So we've encircled a net of 0 current. Where if we look at IC, if we go in this direction again, well, our mu naught I encircled, due to our right-hand rule, is going to be equal to negative I, but the magnitude of that is asked us to rank the magnitude, so it's just going to be equal to I. And because our direction of Amperian integration is not told for us, we selected this, and our ID is going to be equal to I plus I, or 2I. And let's look at another quick check. We'll check evaluating our integral of B dot ds for when we're looking inside the wire. Again, we're comparing our I encircled. Our I encircled for loop D, we've encircled our entire current. So our ID is going to be equal to IC. The B dot ds is going to yield the same I. So our magnetic field we know will be less out here at D, but the closed integral of ds will be greater. So the closed integral of B dot ds for loop D and loop C is the same. If we compare loop A and loop B, we're encircling somewhat less of a current, right? This current, our closed integral of ds, that's this circumference. This is less, as is our current that we've encircled is less. So we have ID is equal to IC. However, IA is less than IB, which is also less than IC. If we look more closely at IB, IB would be equal to what? It would be equal to J times pi RB squared, where our J is I over pi R squared. So that would be times our pi RB squared, where this is our RB and There's our R. So that's it for this video. We'll do examples in the next video.